Hello, everyone. Good morning, good afternoon, and good evening. So this is another webinar in the UK Quantum Fluids Network series. So today's speaker is Ruchi Nomura from Hokkaido University in Sapporo. So Ruchi, when we're ready, you can start your
Eh,
presentation.
Yeah, thank you, Dima. It's my great pleasure to present our recent result on dripping of superfluid helium-4. My name is Ryuji Nomura at Hokkaido University. And this work was done in collaboration with Professor Tani Aoki and other graduate students in my group. And I have several publications related to this webinar. Okay, let me start from the introduction. And let me explain the experimental setup. We have a glass dewar, and we made a superfluid helium-4 by the evaporation cooling. And we prepared a small cup, and we scoop this liquid into this cup. And due to the superfluid film flow, superfluid helium-4 drips from the bottom. And our temperature was 1.6 Kelvin. And I examined this kind of oscillation of the pendant droplet and this dripping process. And the reason that we have such kind of film flow is due to the complete wetting of a superfluid to any kind of a solid surface. Or it means that the contact angle alpha is 0 to any kind of surface for the superfluid. And let me explain the complete wetting first. And here is a substrate, and this is a liquid droplet, and this alpha is a contact angle. And this alpha is 0 for the superfluid, and it spreads over the solid surface. And this is a complete wetting. And this happens because interatomic interaction between helium atoms much weaker than the interaction with the substrate. So it's strongly attracted by this solid substrate, and it spreads over the flat surface. But if we scoop our liquid, superfluid liquid into this cup, it climbs up the wall due to the complete wetting against the wall, against the gravity. And the thickness of this film is order of 30 nanometer. And it forms the same film, and it drips from the bottom. And if this liquid is a classical liquid with viscosity, it cannot go through such a thin film, but it's a superfluid, so it can flow freely through this thin film, and it drips from the bottom. And I recorded the motion of this droplet by a high-speed video camera. And in our case, diameter of this cup is 30 millimeter, and the cup has a hemispherical bottom surface like this. And let me explain what we measured. We measured the length of this droplet. And we also measured the volume of this droplet. And since we observe the droplet only from the one side, I assume that cylindrical shape to estimate this volume. So we measure the length of the droplet and also the volume of the droplet as a function of time. Okay. And we also modify the bottom shape of this cup in order to control the edge motion. And here is bare cup, hemispherical surface, and I also prepared the bottom shape like this. I glued the cylinder on the bottom. And for the bare glass cup and the wide cylinder, the droplet moved in this way. As you see, the droplet edge oscillates along the surface as that the droplet oscillates in this vertical direction. So this edge is also moving. And this edge moves freely because the cup surface is already coated by the preformed superfluid helium. So it reduces the effect of pinning. And due to disappearance of pinning, this edge is moving freely. So this free edge motion of the droplet is very specific to superfluid. And in this case, we saw several anomalous behavior. And we made a bottom shape in this way too. I grew that narrow cylinder of about 1.5 millimeter. And in this case, as you see, the edge of the droplet is pinned at the corner of this cylinder. And in this case, the behavior of these droplets is similar to that observed for the water. So in this case, I don't see much anomaly. But in this case, I saw many anomalous things. So next, let me explain the anomalous oscillation of the superfluid dependent droplet. Okay, this is for the bare cup or the wide cylinder case, this. And this is for the narrow cylinder case. And in both cases, pendant droplet oscillated with a high amplitude and minimal damping. Damping is very small. And this is due to the superfluidity. And this bare cup and wide column, as I said, the droplet edge also oscillates. So this oscillation is a quadruple oscillation in the presence of the wall. And it's oscillating this way. And you see that oscillation period is nearly time independent. But during this oscillation, we also measure the volume, and the volume is increasing like this. So the oscillation period, TO, is time independent, and it means that it's independent of the volume. And this kind of volume independent oscillation is very strange, and I call this anomalous to zero. But for this pinned case, as you see, oscillation period becomes longer, like this, as that droplet volume increases. So in this pinned edge case, oscillation period TO is a volume dependent, and this is similar to the oscillation of the water droplets. So I call this a normal to zero. Okay, so let me first explain the anomalous case in more detail. And this is the length of the droplet as a function of time. And I also measure the volume of the droplet. And here is a downward stretching of the droplet. And this is a pinch off. And after the pinch off, the remaining pendant droplet on a substrate start to oscillate like this. And this is nearly time independent. And this stretching is another pinch off. And the time interval between two pinch off, I call this a dripping period, tau. Dripping period is the time interval between these two pinch off. And during this oscillation, the volume steadily increases like this. So from the slope of this volume increase, I can measure this flow rate V dot. And as I said, in this free edge case, this time-independent oscillation means that the volume-independent oscillation. So I call this anomalous to zero. And let me compare this with oscillation with the water droplet when it oscillates during the dripping from the faucet. This was examined by Kyono and others. This is for the water, and it oscillates in a short period when it's small, and as it increases, the period becomes longer. And this is non-behavior. It should show that the size-dependent oscillation period for the water droplets. And this is consistent with this kind of expression. This is the oscillation frequency of the spherical free droplet without a wall. And the deformation from the sphere is specified by this spherical harmonic function, YKL. And as you see, the radius of the droplet here. So this means that the larger droplet should oscillate slowly. And this is a non-behavior, but the superfluid dependent droplet behaved quite differently from this non-behavior for the free edge case. But for the pinned edge case, using the narrow cylinder of the 1.5 millimeter, as I said, that the edge was pinned. For this case, it's oscillates in a short period when the volume is small. And as the volume increases, this period becomes long. So as I said, that in this pinned case, it has a volume-dependent oscillation, and it's similar to the oscillation of the water droplet. So I call this normal 2-0 mode. And from this oscillation, I measure this oscillation period. Okay, let me show. This is oscillation period TO for the free edge case. And this is a pinned edge case. And these points are the time evolution of this oscillation period as a function, time evolution of the oscillation period at various flow rate. So this is a high flow rate, so it drips in a short period. And this is a low flow rate. It's like this. So depending on the flow rate, the time evolution of this oscillation period was different as a function of time. But if we plot this TO as a function of the volume of the droplet at each time, as you see, it collapsed on a universal curve for this free case and also this pinned case. So this collapsing means that the influence of the flow rates or the influence of the evaporations are neglected. And this is really the correct volume dependence, I think, because it's collapsed on the curve. And for this free edge case, it has a nearly volume independent oscillation period. And maybe we have a slight increase, so it has a shallow minimum around here. So it's a non-monotonic and nearly volume independent around here. And this kind of motion is specific to the superfluid, and I call the anomalous to them. But for this pinned case, the oscillation period increases monotonically as a function of the volume. So it's a volume dependent. And this motion is resembled to the classical fluid like a water. And I call this normal to them. And this is a overall dependence of the oscillation period on the volume by using a various diameter of the cylinder. So we have many diameters of the cylinder. And for the narrow cylinders, the edge was pinned, narrow cylinder. And in this pinned case, it has a monotonic increase of the oscillation period as a function of the volume. So these are normal behavior. And for the wide cylinder of the 6 millimeter or 5 millimeter, or the without a cylinder, bare curve, it has a non-monotonic dependence like this for the free edge case. And in between, we have an intermediate behavior. So by changing the diameter of the cylinder, we observe the systematic variation from the normal to the anomalous oscillation behavior. And I think these changes are related to the edge motion of the droplet along the surface. So next, let me explain why we have such an anomalous oscillation. And this is my current understanding. Let me show the stability of the pendant droplet as a function of the bond number, BO. Bond number it's same as the volume dependence as a function of the volume. And in a lower row, we have an ordinary case, ordinary boundary condition, like the alpha equal non-zero and or the pinned edge case. This is ordinary case. And at large volume, we have a pinch of instability. And below this volume, any small droplet can exist stably. So below this volume, any of the small volume droplets are stable in this ordinary case. But this in this, I call magic condition, but anyway, in this special case, alpha equals 0 and H moves freely. Only in this case, situations are quite different. And in large volume region, we have a pinch of instability. But we have another instability in a small volume region. It's a Rayleigh-Taylor instability. And in this volume region, the pendant droplets are not stable, but uniform thin film is stable. And superfluid pendant droplets can exist only in the intervening region between these two instabilities. We have a stable pendant droplet only in this region between these two instabilities. And if near this instability, the restoring force for the oscillation disappears, then we expect to have the divergence of the oscillation period in these two limits. In these two limits, the oscillation period should be very large, at large and small volume. So in the intermediate volume region, we should have a minimum in the oscillation period, and that may explain that anomalous behavior. And that's my interpretation of the anomalous behavior for the superfluid pendant droplet in alpha equals 0 and the free H case. And recently I found a good theory. It's recent theory, 2023. And Tang and Zhou calculated the oscillation frequency of a pendant droplet in a wide range of the contact angle alpha under the pinned and non-pinned boundary condition at arbitrary KL modes. And this is their calculation of the scaled frequency of the 2L mode as a function of the bond number, but it's same as a function of the volume. For the free H case and the pinned H case. And as you see, in most of the cases, this has a monotonic decrease like this. Most of the cases, it's decrease monotonically. But we have one exception. Only in the case of this alpha equals 0 and the free H case, it has a non-monotonic dependence like this. And I think this is related to our observation of the weakly volume-dependent oscillation or the anomalous mode. And I converted their calculation to the superfluid helium case. And they are those two lines are their calculation. Okay, first, let me show the pinned edge case, and diameter is 1.9 millimeter or 1.7 millimeter. This is their calculation, black line. And it's reasonably agree well with our observation of about 1.5 or 2 millimeter diameter, like this, for the pinned edge case. And this is a normal behavior. And the free edge case, they also reproduce this kind of volume independent oscillation. Because it's volume independent, because at large volume, we have a divergence in the oscillation period due to the disappearance of the restoring force at large volume. And we have the same situation at a small volume. And in between, you should have a minimum. And around the minimum, it should show that it should show the weak volume dependence. And the agreement with our observation for the wide crown is reasonably good. So I think their calculation explains our anomalous oscillation. And I think that the cause of the anomalous oscillation is the volume, the cause of the anomalous oscillation is the existence of the another instability at the small volume. And that is relevant only for the superfluids, free H case and alpha equals. So that's my current understanding of the anomalous behavior. Okay. So I explained you the oscillation of the superfluid pendant droplet. next, let me explain the dripping period of the superfluid droplets. And I observed the robust discretization. Okay, this is a length of the droplet as a function of time in a very large time scale. This is about 8 minutes. So 8 minutes we observe the dripping from just after scoop to the end of the dripping when the cup becomes empty. And during this process, flow rates are gradually decreasing. So around here, it oscillates once around here, but the flow rate gradually decreasing. So around here, it oscillates twice. And around here, it oscillates 3 times due to the lowering of the flow rates, gradually decrease. And around here, it oscillates 4 times. Here, 5 times. Here, 6 times. So from this, you can see that the timing of the dripping is completely determined by this oscillation. It's determined by the number of the oscillation. So I measure the dripping period, tau, as a function of time. And at the same time, we observe the flow rate, d dot. As I said, the flow rate gradually decreases like this. Flow rate decrease. So the dripping period increase like this. But this period increase was not smooth. But you see that the step-like change in the dripping period tau. For example, around here, it has nearly the fixed dripping period. But the flow rates are gradually decreasing around here. And around here, it jumps to the next stable period. So it has a step-like change. And these black lines are the plot of this function. And they agree well with the stable oscillation period. And the n corresponds to the number of the oscillation. And here I show the tau as a function of time, but next I show this tau as a function of the flow rate. Okay, dripping period tau as a function of the flow rate. I think this is a more essential plot. And you see, by decreasing the flow rate, it has a step-like change in the dripping period. And n corresponds to the number of oscillation. Here is a zoom up. As I said, the flow rate has a nearly fixed value, even if the, sorry. As I said, we have a fixed value of the dripping period tau here. Even if flow rate B dot is changing in this range for the free edge case. So fixed period at varying flow rate. So we have a very robust discretization of the dripping period for this free edge case. And let me show the trajectory of the length of the droplets for the many of the oscillation like this. The flow rates are gradually changing, but you see that bunching of the trajectory of the droplet oscillation like this. And lower row is a histogram of the dripping period, tau. And due to this bunching, we have sharp peaks in the dripping period like this, due to this bunching of the trajectory. And these are black lines as a plot of this function, and the peak position agree well with this expression. So this means that the separation of these peaks are equal. So they are many peaks appeared and their separations are equal for the free edge case. And this kind of a regular behavior is quite anomalous. And let me compare with the dripping of the water from the faucet. And this is measured by Kiona and others. And the dripping period of tau as a function of the flow rate for the water. Here's a zoom up. And as you see, the dripping period has a wide distribution like this, even if the flow rate is fixed at this value for the water. And this distribution was known to be caused by the chaos for the fluid motion. And this is a very well-known example of the fluid chaos. It has a wide distribution and it looks a little bit irregular. And this is quite different from our observation. Let me show our observation again. This is for the helium. It has a fixed dripping period, even if the flow rates are changing in this region for the superfluid. But for the water, it has a distributed or wide distribution of the dripping period, even if the flow rates are fixed at this value. So the behavior of the superfluids dripping was quite anomalous in this sense. It's very different from the non-behavior. But if we do the same thing by using a narrow cylinder of 1.5 millimeter, like this, in this case, the edge of the droplet was pinned. And in this case, dripping period as a function of time, and we don't see a step like this. And we have a wide distribution. And this is tau as a function of the flow rate, so we don't have a discretization. So in this pinned case, the dripping behavior was similar to the dripping of the water. So this is not so strange once it's pinned. Okay, let me compare these two. This is a pinned case, and I plotted the trajectory of the oscillation. And in this pinned case, it's quite irregular. But for this bare cup, the edge can move freely. And in this case, you see the bunching of the trajectory. Now, flow rates are gradually changing, but the change of this trajectory was not smooth. It moved to another step like this. So it keeps this dripping period, even if the flow rates are changing. Okay, let me stop here. So the free edge case, the bare cup, and we had anomalous oscillation, and we saw the bunching of the trajectory, and this bunching makes a peak in a histogram of the dripping period. This is anomalous. But once that the edge was pinned, the trajectory became quite irregular, and we don't see any reproducible peak for the histogram. Tau has a wide distribution. So these two behaved quite differently. Okay, this is overall dependence of the histogram tau. And for the pinned case, it has a wide distribution, and we don't have a discretization for the pinned case. But for the free edge case, like a wide diameter cylinder, 6 millimeter, or bare cup, we had a sharp discretization of the dripping period. So it behaved quite regularly for the free edge case. And these are the intermediate. So the peak structure becomes broader and disappeared eventually. So this is a systematic variation of the dripping behavior. Okay, let me show some more analysis. This is our recent analysis. Okay, so far I showed you when the flow rates are gradually changing, but from now I'll show the trajectories at nearly fixed flow rate. And I show the 100 of the trajectory at the nearly fixed flow rate. And for the free edge case, I show the droplet volume as a function of the time during the oscillation of the droplet. And you see that the droplet volume has a little bit distributed like this. They don't follow that exactly same path, but they had a distribution. I mean, volume had a distribution for the free edge case. And the pinned edge case, this distribution seems to be wider like this. But anyway, in both cases, we had a irregular behavior for the time variation of the volume. And I plot this length of the droplet as a function of the volume. And in this case, the trajectory also has a distribution like this. for the free edge case. And for the pinned edge case, the distribution was more broadened, so it's more irregular. When we plot L against the volume, but when we plot this length L as a function of time, the distribution disappeared and they followed that exactly the same trajectory like this. And it has a distribution only in the final stage of this dripping for this free edge case. But for the pinned edge case, even if it's plotted against the time, it has a irregularity. So for this free edge case, somehow the effect of the fluctuation in the volume was completely disappeared when it's plotted against the time. And I think this is due to the anomalous oscillation of the droplet. Okay, these are the same graph. Yeah, same graph. And I will show the same data, but in a different way. I will show the attractors in a phase space. So L dot and L for the 100 trajectory. So for this, please look at this pinned case first. I show the 100 of the trajectory in a phase space during the oscillation. And as you see, it traces the different paths. So this is quite irregular. But when we plot the trajectory for the free edge case, it's like this. It's 100 of the trajectory. And it's followed that exactly the same traces. That we have a little bit scattered around here. Okay. This circulating part corresponds to the oscillation of the droplet. And this stretch part is a necking process of the droplet. And around here, it's pinch off. So near the pinch off, we had a little bit scatter in trajectory. But after the pinch off, everything was reset. And it started to oscillate along the same trajectory like this. So this again somehow shows that the influence of the fluctuation in the volume was erased after the pinning. So free edge case, we have a regular trajectory overlaps, and the influence of the volume fluctuation was eliminated due to the volume independence or the anomalous oscillation. But for the pinned case, its attractors are quite irregular. Trajectory distributes a lot. And the influence of the volume fluctuation seems to be enhanced due to the volume dependence. So again, these two behaved quite differently. And my question is that can we regard this kind of regular superfluid dripping as a new form of continuous time crystal or not? And obviously, the system spontaneously determines the dripping period without fine-tuning from the outside under the continuous driving. In this case, driving of the dripping is the input of the flow. So this B dot flow rate is at the strength of the driving of the dripping. So and the stepwise change in the dripping period like this clearly shows that its stability against the fluctuation in the flow rate and other external perturbations. And in order to keep this dripping, we need to supply the mass and the energy into the droplet. Otherwise, it stops. So we have to keep driving by the input of the mass and the energy into the droplet. But even under such a driving, it has no heating because it's superfluid. And these are the some of the requirements for the continuous time crystal. And they are satisfied in superfluid dripping. So this supports the idea that the superfluid dripping can be viewed as a time crystal or the analogous system of the time crystal. But I have some concerns, and my concern is that the system is not uniform, but it's a droplet. And they have no modulation in the space, but only in the time direction we have a modulation. So it's a one-dimensional time crystal. It has too much input and too much output of the particles, because about 90% of the particles are replaced by a single pinch-off. So it's a highly non-equilibrium system and maybe too much open system. So I a bit hesitate to say that it's a phase or it's crystal. And this may be the classical type of the dynamics. So I'm not quite sure that I can simply call it a time crystal, but it satisfies some of the requirements. So it can build as analog. It can be built as analog of the time crystal. But I appreciate any comment on this interpretation. I'm not quite sure, so I appreciate the comment. Okay. Finally, let me show the Nater model of the pendant droplet. Okay. On a wide cylinder of the 5 millimeter, we observe this kind of motion, horizontal motion of the droplet. So it's oscillate horizontally. And I think this is a 1-1 mode or the Nater mode. And the 1-1 mode is a dipole mode, and it's a zero frequency mode in the presence of the spatial translational symmetry. So this omega is 0 when k equals 0. So that's a zero frequency mode. And this kind of motion with the pendant droplet has never been observed in the classical fluid because they have a strong pinning, but it's a superfluid and it's completely covered by the thin film, and it's freely move along the surface. And I think that leads to the realization of the vertical mode for the classical fluid. Virtual mode of the classical fluid was realized in a superfluid. So let me show you some analysis. This is a horizontal position of the droplet as a function of time, and it's oscillate in this way. And I measure the volume of the droplet at the center. And from the slope of this oscillation, we can estimate the horizontal velocity of the droplet. The horizontal velocity Vx decreases like this during the oscillation as a function of time. But when we multiply this volume of the droplet, it keeps nearly the constant value. And this means that during the droplet oscillation, the initial momentum is conserved. And this supports that idea of the interpretation of the observed motion. This supports the identification of the horizontal mode as a Nater mode, because it should keep the momentum. Yeah, this is support. And I'm interested how the Nater mode was excited. And let me show this graph. This X is a former pinch-off position. And this vertical axis is a horizontal momentum. And this graph shows like this. Okay, when the droplet was pinched off around the right corner, the subsequent motion of the droplet is to the left. When the droplet was pinched off around the left corner, subsequent motion of the droplet is to the right. And when it's pinched off around the center of the cylinder, it doesn't move much. So this means that anisotropic recoil from the corner after the pinch off drives the droplet motion. And the droplet keeps moving, keeps oscillating along the surface by conserving that initial momentum. Initial drive by keeping that initial momentum due to this recoil. So this also supports that the observed motion is a Neta mode, I think. And how the droplets reflected at the corner is also interesting. So let me show this. Okay, this red is at the left edge of the droplet. And this blue is a right edge of the droplet during the reflection at the corner. So it moves like this. Okay, let me stop. So around here, right edge reached the corner and it stopped moving at this time. But left edge is still moving. That means that the droplet is distorted when it reaches the corner. Around here, the left edge start to move, but the right edge is not moving at this time. So this is the release of the distortion. So this means that the droplet is distorted at the corner, and the distortion conserves the distortion transforms the kinetic energy of the droplet motion into the distortion energy, and by releasing the preserved distortion energy into the kinetic energy, it's induced the droplet motion to the opposite direction. So this is how the droplets are reflected at the corner. So I think it's like a reflection of the ball at the wall. Okay, when the ball hits the wall, the kinetic energy is transformed into the elastic energy by the distortion. And by reducing the elastic energy into the kinetic energy, it's reflected. So in this case, distortion energy is stored as a surface energy. But anyway, it transforms the kinetic energy once and releasing that stored energy into the kinetic energy. And that's how the droplets are reflected at the corner. Okay, this is my summary. I observed the pendant drop. I observed the superfluid pendant droplet, and they oscillate high amplitude and minimum damping due to the superfluidity. And for the bare cup and wide cylinders, each of the pendant droplet moved freely, and it shows the oscillation period independent of the volume. So this is quite different from the classical fluid. So I call the anomalous to them. And the dripping period was robustly discretized, and this is also different from the non-behavior for the water. But for the narrow cylinder, the edge was pinned, and it shows a volume-dependent oscillation. And this is similar to the water oscillation. So I call it normal to zero. And it has a wide distribution, and this also resembles the dripping of the water. The wide cylinder, I observed the Neta mode that's freely oscillate along this bottom surface. Okay, that's it. Thank you for your attention.
Thank you, Ruchi. It was very interesting talk. So, do we have any questions? Anyone? Okay, I'll ask a question. So, the quantization of the period.
Yeah.
So, is it dependent on the size of the cylinder, or is it?
Yeah.
Okay. So, do you have any sort of thoughts about how it?
Yes.
Yeah.
Okay. Yeah. This oscillation period. No. This peak separation depend on the diameter of these cylinders.
Mm-hmm.
And this is because the oscillation period of the droplets yeah, this is a not dripping period, but this is oscillation period of the droplet. And this also depend on the size of the cylinder.
Hmm.
So the separation of the peak is determined by this oscillation period because the separation, because the peak is determined by the number of the oscillation. So yeah, there's peak separation corresponds to the oscillation period for these droplets.
Okay, I see. Yeah. Any other questions? And then, so for the uh, translational mode,
Yes.
so how is the motion initiated? So is it well, because in principle the system is symmetric, so how would the droplet start moving to begin with?
Yeah. Okay. When it's pinched off, it's like this, and the recoil of the pinch off, by the recoil of the pinch off, the droplets, remaining droplets start to spread over the bottom surface. But during this spreading, when we had a corner, it pushes this side. So
Hmm.
the recoil from the corner is anisotropic. Okay, this direction it cannot move due to the pinning, but this direction it can move freely. So anisotropic recoil induces the initial kick of this droplet motion. That's my interpretation. And you may be think that why, okay, when it's pinch off around the center, it doesn't move much.
Hmm.
And
Okay, yeah, makes sense.
yeah, but in this case, if it's really not moving or it's moving to this along this side, I cannot distinguish between these two because I only observed from the one side. So
Hmm.
around here, it's not moving, but it may be moving along this side.
I see. Yeah, because you're measuring in
So
in
yeah,
one
yeah.
dimension only. Okay.
So yeah, it's what we see is only that the projected motion uh, to this our observation. So
All right. So yeah, any more questions? Well, I don't see any more questions. So thanks a lot, Ruji.
yes, yeah,
Thanks a lot for staying late
yeah.
for this webinar.
So
And yeah,
it was
hope to
nice. Thank you very much.